This lesson, we'll try and explain and give some examples of functions and function notation. For many of you, your experience might be working with equations. So that's going to be my starting point. I'm going to start out by talking about equations and then how functions relate to equations. Very common type of equation would be one equation with two variables. Most commonly, in math, we use X and Y. And of course, eventually, and I'll even do that now and later on, these kinds of equations oftentimes lead to graphing and all that kind of stuff. But let's for now talk about what actually is this equation. And once we understand that, then we can go to function notation and hopefully it'll be very clear. Just for fun, what if someone gave you this equation and they asked you to solve this equation? All right, that's pretty common in the world of math. You're given an equation, you're asked to solve it. But what's interesting is, because there are two variables in one equation, normally, when you first learn to solve equations, you may have had something like this. This is an equation. Of course, here there's only one variable. So the way we solve this is we basically did some algebra to get x by itself on one side. So in other words, if we subtract x from both sides, we add 3 to both sides, divide both sides by 4, and you get x equals 1. X equals 1 is the solution to this equation. And by solution, let me tell you now, because it becomes important. Solution is what's the value of x, what's the number for x, that if I plug it into my equation, it makes this equation true. When you first learned to solve equations, you were probably told to check your work, check your solution. Checking your solution means you take your answer and you plug it back into the original equation, and it better work. If it doesn't work, then you made a mistake in your math. So a solution is the value of x that makes this true. The problem is I have two variables here. Let's do this. How about I just say, just to help us out, I'm going to take one of the variables and I'm going to, just for now, so we can make some progress, I'm going to say, let's just assume x equals 0. So we're going to define one of the variables. Go ahead and give that variable a number. Now, if x equals 0, so I plug in 0 for x, then I actually can solve this equation. Because when x is 0, y equals 1. So it's interesting how if I go ahead and assign a number for x, then I can solve the equation and I get this value of y. In a sense, what's going on here now is really, I have two solutions, or the solution has two parts, right? Because I have two variables here, my solution is going to be a number for x and a number for y. And that's what I have here. I can call this a solution, right? Because if I plug in 0 for x and 1 for y, this equation is true. As a matter of fact, and you probably know this, for these kinds of problems, oftentimes they like to express this kind of solution in what they call an ordered pair, right? An ordered pair is two numbers inside of parentheses separated by a comma, and we always write the value of x first and the value of y second. So for this one, So we say 0, 1 is a solution to this equation. Now what's interesting is, are there any more solutions to this equation? It's funny, over here, there's actually only one solution. There's only one value of x that's going to make this equation true. But here, and the key is because I chose this number for x and then found the y and then came with my solution, what if I had chosen, instead of x equals 0, what if I instead decided I want x to be 1? We know what happens is if I plug x in to my equation, if I plug 1 in for x and then calculate y, y is 3. As an ordered pair, I say, here's another solution to this equation, 1, 3, right? And by solution, that means if I plug in 1 for x and 3 for y, that works. So now I have here 2 solutions. As a matter of fact, theoretically, how many solutions would this equation have? Well, theoretically, an infinite number of solutions, because we could just keep choosing different values of x all day long and come up with the value for y and have another solution. Matter of fact, sometimes, especially if they give you this, a lot of times they'll give you this kind of equation and they'll sometimes want you to graph it. One of the ways you probably first learned to graph was they had you make a data table, right? And that's where they, so like a T, you have 2 columns. And what they had you do was they would have you choose a value for x. In other words, if I chose x to be 0, then you plug it in and you calculate y, and y is 1. And if I chose x to be 1, I've already done this one, y is 3. I could choose x to be -1. So when I plug in -1 for x, I get -2 plus 1, looks like -1. Just for fun, let's do a couple more. If I plug in 2 for x, looks like y is 5. And if I plug in -2, -4 plus 1, -3. So here, in a sense, I've listed 5 solutions. And really, if I wanted to, off to the side, I could write each of these as an ordered pair. As a matter of fact, just for fun, although we're going to discuss graphing later, I might go ahead and use these and create a graph, and we'll see what happens. This thing is actually called a linear equation. Linear equation means there's no exponents on the x or the y. And when I graph this, if I can graph it correctly, it should be a straight line. Because when you graph a linear equation, you get a straight line. So let's say 1, 2, 3, 4, 5. So like here's 5. So right, x-axis is the horizontal axis. Up and down is the y-axis. I assume you all remember how to graph, right? Let's see how close we are. 0, 1. 0x, 1y. 1, 3. x1, y3, 1, 2, 3. Because this is 5, -5, -5. -1, 1. -1, -1. 2, 5. x2, y5. And then -2, -3, -2, -3. Now, of course, I'm drawing this freehand. Theoretically, these points should all be pretty much in a straight line, and they look pretty close. And if I were to draw the graph, I would connect all the points. As a matter of fact, sometimes on the graph, they will even label this y equals 2x plus 1. Because in a sense, you know what this graph, this line represents? This line represents all the solutions to this equation. In other words, I could choose any point on this equation. If I went right here and I looked up the value of x and looked up the value of y for that point and plugged it in here, it would work. And in the same way, if I went and chose this point over here and I plugged in that value for x and this value for y into my equation, it would not work. Why? This point is not a solution. Why is it not a solution? Because it's not on the line. All the solutions to that equation are on this line. And of course, you notice this line goes on forever and ever, and that's why we said we have an infinite number of solutions. All right, so with that as a foundation, let's talk about what in the world is happening when we go to function notation. So this is traditional two variables, in this case a linear equation, pretty common kind of thing you learn in math when you're starting to work with equations. Function notation. So let's go back to the equation we were working with above, y equals 2x plus 1. Now let me talk about some notation, because this sometimes helps to understand sort of how a function sort of works or why they like to use functions. Sometimes people in math like to describe the way an equation like this works. They like to describe it in two different ways that I've seen. And the key is because there are two variables. The first way is a lot of times people will call x, they like to call it the independent variable. Independent means there's no constraints. It's not dependent on anything. Basically means you can make x whatever you want it to be, which is in a sense what we did up here, right? I was just choosing whatever I wanted for x. It's almost like x is independent. I can choose anything. There's nothing, no constraints, no rules. I can make x anything. It's independent. But what happens is once I choose a value of x, what happens? Based upon the equation, that sort of locks in or defines what my y is going to be. So if x is my independent variable, they call y the dependent variable, because the value for y is going to depend upon what I choose for x. So that's one way they like to talk about how equations work and how these sort of variables interact with each other. The second way is it's the same idea. Instead of independent variables, sometimes people like, this is maybe even simpler language, they like to call x your input, or an x, you're going to choose a number for x, and that's like, it's almost like sometimes you have this like a black box, you have these diagrams. Here's your equation. Your equation is y equals 2x plus 1. What do? I'm going to input, I'm going to choose a value, a number for x. So that's like my input. It goes into my box. This box has an equation. The equation takes that value of x, applies it to the equation, and in a sense, it spits out a y, and they like to call y the output. So that's sort of a conceptual, practical way to think of really what an equation is doing. In our case, we choose a value for x, and it produces a value for y. Well, I explained that because function notation sort of is that same idea, and you'll see later on how that concept makes a difference. Now here's the most common function notation that we're going to use in math. We'll probably use this 90% of the time. There can be other types of function notation, but this is the most common. Now, possibly up until now, when you're doing algebra, if you saw that, you might think, oh, this means f times x, right? Because a lot of times when you have something in parentheses, that means multiplication. All right, that's not what we have here. This is called a function notation, and this represents a function. Matter of fact, the way we normally pronounce this, we say f of x, f of x. This has nothing to do with multiplication. Matter of fact, what happens is this f is like the name of the function. It's almost like we have a function f. And the x, whatever's inside the parentheses, the variable actually in the function. So for instance, we've been looking at this equation with x and y. If I want to rewrite that as a function, it's very simple. Matter of fact, the equation, this expression stays the same. The only difference is instead of writing y, we replace it with this f of x. Matter of fact, one of the most important things you need to remember from now on when we're working in math and with functions is that f of x and y are really the same. Sometimes you'll see me solve problems and it'll be in function notation, and for whatever reason, I want to switch it to y because maybe it helps me to understand it better. Maybe sometimes there's an equation with y and it gets changed to f of x. F of x and y are like interchangeable. They go back and forth all the time. Matter of fact, sometimes you'll be given a function and you'll ask to graph it. And then they give you the graph, and a lot of times you'll see the old traditional XY graph, and you're thinking, wait a second, I have a function here, I don't have a y here, why am I graphing y? Well, because f of x and y are the same. I mean, other times you're graphing a function, and they'll label the axis f of x. Well, y and f of x are interchangeable. They can mean this, they mean the same thing. You can switch them back and forth. So the key is to take an equation and to sort of turn it into a function. It's simply a matter of notation. We're not really changing what's happening. We're just changing the notation. So for instance, now just to compare how this works, earlier we gave an example of, let's say, if x equals 0, then y equals 1, looking at the equation. Well, in the same way, if I want to look at the function and I decide for the function, I want x equals 0, then f of x would equal 1, right? If I plug in 0 in here for x, so now the question is, okay, we've changed y to f of x. We haven't really changed the expression. So what's the whole purpose of even using this function notation? Well, I guess I would say as you go on in math and things are more complicated, function notation is a way to make things sort of cleaner and neater and more precise. And you're going to see in a minute one of the big ways that we use function notation to sort of make things a little easier in terms of writing and knowing what's going on. Matter of fact, I may use this problem right here. So here's an example of comparing with an equation and the function. You know what we like to do? What they do, if you have a function and you say if x equals 0, then fx equals 1, a lot of times when they have, or most of the time, when they define the value for x. They don't write it this way. They'll just say f of 0. So that's always the way you pronounce it. You say f and then of whatever is inside the parentheses, f of 0. F of 0 means what happens is you always take this and you compare it to your original function. My original function was f of x equals 2x plus 1. You know what this notation is saying? This notation is saying I'm looking at the function f. This is my function f. I know my function f has the variable x in it. Matter of fact, whatever variable is inside the parenthesis, that's the variable you're going to find in your function or in the expression. So f of x equals 2x plus 1. F of 0 says every place I have an x in my expression, in my function, I'm going to replace it with 0. Or you could say you're going to substitute 0 in for x. So my function, f of x, my function f is 2x plus 1. F of 0 means every place I have an x, I replace it with 0. So it becomes 2 times x, now it becomes 2 times 0 plus 1. So when I work this out, it's 1. So in a sense, if x is 0, f of x equals 1, a better, cleaner, more clever way to say it, f of 0 equals 1. F of 0 means take your function f, put in 0 for x, and when you do that calculation, it equals 1. Just for fun, what if I said what does f of 2 equal? F of 2 means you go back to your original function. Every place you have an x, you replace it with 2. So 2x plus 1 becomes 2 times x. But I'm going to put in 2 for x plus 1. 5. F of 2 is 5. If I go back to my previous chart, remember when I said, well, let's set x equal to 2. What does y equal? 5. All right, done the same thing. F of 2 equals 5. When x is 2, the function is 5. And the function, in a sense, is just like y. Now, once you start using this function notation, you can start to do some interesting stuff. As a matter of fact, once again, so this is the starting point for doing all this stuff is they have to give you the original function. And let me just say it now. 90% of the time, your functions are going to look like this, but functions don't always have to be called f of x. So this, in a sense, is saying the function f, and it has x in it. G of x, now this function, I'm going to call this function g. Now the variable is still x, so this function g has an x in it. Matter of fact, you don't always have to use the variable x. We're going to, like 98% of the time, but you may occasionally have some kind of problem where your function is g of a. Once again, so we call this function g. Whatever's inside the parenthesis is going to be the variable that's in the expression. So you notice there's no x's anywhere because this is saying, hey, a is going to be my variable. So when I look at this expression, obviously a squared minus 2a, I have to have a's in here. So all three of these are functions. The name of the function will sometimes change. Sometimes they use a different variable. All I'm saying is, for now on, almost every time when I do problems, we will use f of x. That's the most common. When you get the homework and stuff, you will see some other types of functions. All right, that was a little side road, but so let's go back. I'm going to rewrite it here. So here's the function I'm given, f of x equals 2x plus 1. Now, how about if they gave me this question? F of x plus 1 equals what? All right, the whole idea of function notation, the whole idea of this f of x is f of x plus 1 says, I go to my function, I start looking at it, and every place I have an x, what do? I replace it with x plus 1. That's what function notation allows you to easily designate or signify. So f of x plus 1 is, here's my f function, 2 times x. 2 times x. However, I'm not going to write x. I'm going to substitute x plus 1 in for x. So instead of 2 times x, I have 2 times x plus 1. And then the rest of my function is just plus 1. So f of x plus 1 equals this. Now, normally when you have this kind of thing, they always want you to try and simplify your function. So I'm going to multiply out the parentheses and then combine like terms. So if I distribute the 2, so this is 2x plus 2. I got the plus 1. So now finally I end up with 2x plus 3. So what we're saying is f of x plus 1 equals 2x plus 3. What if we say f of x squared equals what? Once again, the same principle. Talking about the function f. Here's my original function that I'm working with. And they're saying f of x squared, which means I go to my function. Every place I have an x, I replace it with x squared. So I have 2 times x, but instead of x, I'm putting x squared plus 1. So f of x squared equals 2x plus 1. And then it can get sometimes a little crazy. Let me just do a couple more for fun. How about f of 1 over x? Well, the good thing is the principle is the same, right? It's all a matter of substitution. I go to my original function, f of x, but now I have f of 1 over x. Every place I have an x, I'm going to replace it with 1 over x. So 2 times x would be 2 times 1 over x plus 1. A lot of times we would sort of make this look a little cleaner and neater and just say it's 2 over x plus 1. And I'll just do one more. What would be f of 2 square root of x? All right, this is not hard, right? Same routine. Go to my function. Every place I have an x, I'm now going to replace it with 2 square root of x. So 2 times x, 2 times 2 square root of x, then plus 1. If I go and multiply these together, 4 square root of x plus 1. Just for fun, let me new function. G of h equals h squared minus 2h plus 5. So my function, I would call this function, this is g. My function is g. The variable is going to be h. So when I look at my expression, of course, it's got the variable h in it. We'll just do a couple real quick. G of 0, what does that mean? You go to your g function. Every place you have an h, you plug in a 0. We can do this in my head, right? 0 squared 0 minus 2 times 0, 0 plus 5. How about g of minus 2? All right, every place I have an h in my g function, I plug in minus 2. I better write this one out. So minus 2 squared, this is a minus 2 times minus 2 plus 5. Gotta be careful with our minuses here. Negative 2 squared is just 4. Now negative 2 times negative 2 is negative 4, but I'm subtracting the negative 4. So when it's all said and done, that's plus 4 plus 5, looks like 13. And then just to get extra messy, what if I said, what is g of h minus 2? So you go to your g function, every place you have an h, you put in h minus 2. So h squared becomes h minus 2 squared minus 2 times h, which becomes 2 times h minus 2 plus 5. Now you have to simplify this. So this is like h minus 2 squared is like h minus 2 times h minus 2. You have to FOIL it. Then this, you distribute the minus 2, and then you combine like terms. I'm not going to take the time to do that because that's just a bunch of algebra, which I think you can do. I just want to give you another quick example of how this function notation works. Now let me go ahead and give you a actually very famous because it ends up getting used. In calculus, when you first learn calculus, you have this thing called the difference quotient, which is really the whole foundation when you start to learn calculus and how to take what we call derivatives. Difference notation is, so if we're given a normal typical function f of x, the difference quotient is going to be f of x plus h, which is interesting. So I got two variables, minus f of x all over the variable h. The reason I show you this is because they're actually going to have some homework problems where they're going to give you a function and they're going to say, based upon that function, calculate the difference quotient. In other words, we'll start with an easy one. For the function f of x equals x minus 1, find the difference quotient. The difference quotient. You notice there's three parts to this. Although the h is the variable, so really in a sense, it's almost like there's two parts. You have f of x plus h minus f of x. Sometimes when I first start to do these problems, I sort of list them just to make it very clear what we're doing so people don't get confused. Let's just go figure out what is f of x plus h. F of x plus h says you go back to your f of x, your f function. Instead of x, you put in x plus h. So if f of x is x minus 1, f of x plus h is x plus h minus 1. Which I can drop the parentheses and just say it's this. Then I have f of x. Well, the good thing is f of x is just my function. don't have to do anything. I'm just going to rewrite it. So now these are the two terms, the two pieces of the top of this fraction. So now let's go and plug everything in and see what happens. So f of x plus h is this right here. Sorry, x plus h minus 1 minus f of x. This is f of x. Now be careful. Since I'm subtracting f of x, I'm subtracting the whole function. I'm going to put f of x inside the parentheses just to make sure I don't mess up, because I'm subtracting the whole function. And then it's all over h, which doesn't change for now. So then what you do is you try to simplify this. In other words, x plus h minus 1, this, since I'm subtracting this parentheses, like that negative gets distributed. So the x becomes negative, and when you subtract a negative 1, and now to keep trying to simplify, if I combine like terms, I have an x term here and a minus x. So x minus x, actually those guys cancel out. I've got an h, and then I got a minus 1 and a 1. Oh, minus 1 plus 1, those also cancel out. So actually I'm left on the top with just h. On the bottom is h. H over h reduces to 1. So for this function, the difference quotient equal to 1. Let's do one more that's a little more complicated. How about f of x, original function f of x is x squared plus 2x. And they're asking once again to calculate the difference quotient for this function. So it's going to get sort of messy. So I'm going to go ahead and do them sort of separately. So you notice once again, I'm going to figure out f of x plus h. So I take my function, every place I have a x, I put in x plus h. So x squared becomes x plus h squared plus 2 times x, which means 2 times x plus h. I need to simplify this. That means I'm going to have to FOIL. Hopefully, you haven't forgotten your x plus h squared means x plus h times x plus h. This I can distribute to 2. When I FOIL this, I get x squared plus 2xh plus h squared plus 2x plus 2h. Now I look at all this and I see if there's not even any like terms. These all have different variables, x squared, 2xh, h squared. So this whole thing is f of x plus h. It's already getting very messy. Then I'll go ahead and write down, so minus f of x, I'll go ahead and write down the f of x just to keep it all straight. So I just recopy my function, which is x squared plus 2x. Now the difference quotient is the f of x plus h, this whole thing here. That's why these problems can get messy fast. That whole thing minus f of x, which is this right here, all over h. Now the main work here is to sort of simplify the numerator. I may skip a few steps because what's going to happen is Let me rewrite this without doing the whole thing. So this minus gets distributed. It's going to end up being minus x squared minus 2x. So I start combining like terms. You notice here x squared and minus x squared. And when you do the difference quotient, this is always what happens. If you've done it correctly, a bunch of stuff actually cancels out. It always happens. So x squared minus x squared, those cancel out. It just end up being 0. 2xh, there's nothing to combine it with. So the 2xh is still here. A lot of times I even mark each of my terms, make sure I don't forget any. Here's h squared, nothing else to combine it with. Here's 2x. Here I've got a negative 2x. What's 2x minus 2x? They also cancel out. And then here I have a 2h. And all that is over h. As it turns out, I have 3 terms on the top. And they all have an h in it. And I have h in the bottom. So I can cancel an h out of all these terms. So the fraction goes away. And it becomes 2x. I'll put the 2 next. And then I'll put the h last. So the difference quotient for x squared plus 2x ends up being 2x plus 2 plus h. Turns out you've got both x and h in here, which happens sometimes. All right, so that's a difference quotient. So in terms of function notation, that's one of the very common problems they're going to give you. All right, so that's a good start on what is function notation and how to do and how to calculate some functions using function notation. I'm going to stop now, and on the next video, we're going to quickly look at a special function called a piecewise function, because we're going to have to use those in our class. So let's stop now, and we'll pick up the next video with piecewise functions.